Yes, thanks, Jingyu, for the introduction. So, already in the previous talk, we see that modern system on chip is more than just CPUs. Well, in practice, they are much more complicated. So, here's the diagram of IMX8, a system on chip used in the automotive industry. The Linux that sits on the CPU is only a tiny box up there. And in this system, there are many more cores that run in parallel with the CPU and running their own firmware. So Linux does not know does have no control over them. It does not even know their existence. And this level of complexity is true for computer as small as system on chip and as large as servers. And to build reliable system software, we need to understand the interaction of all these components. And this is what my group is doing to put out the hardware dumpster fire. And among them, there's one important network that controls the power, clock, and temperature of all these components. And this network runs I2C, inter-integrated circuits. So I2C is a widely used protocol because of its electrical simplicity. The protocol itself is very complicated, but the wiring is simple. It only has 2 wires, 1 clock, and 1 data. And on one I2C bus, there's 1 controller in blue and one or more responder in yellows. And the electrical level on these 2 wires encode these 4 I2C symbols. And on IMX8, the I2C controller is this system control unit. And the responder, it has a dedicated I2C, and the responders are those power regulator, clock generator, temperature sensor, and so on. And for servers, the controller is board management controller, or BMC. It is a slightly more powerful standalone chip that runs its own firmware, but we see the similar level of hardware complexity in the servers as well. And the state-of-the-art firmware implementation for BMC is OpenBMC. Well, it is a Linux distribution. That means behind the scene, there's another Linux managing your Linux machine. Yes, and well, but because that I2C network used the I2C protocol, in an ideal world, the BMC should only just need to implement the standard I2C protocol, and it should be able to drive the I2C network, right? The truth is, the I2C protocol is often banned. There are many devices out there that have quirks, means that part of the device does not follow the I2C standard. So here we show one example. In the middle, this is a standard I2C read transaction. So the I2C controller first transmits the target address, and then a bit indicating this is a I2C read transaction. However, the AS5011 health sensor does it differently. Right. So, and following that bit, the following payload bytes should be supplied by the responder because this is a read transaction, right? But the AS5011 health sensor does it differently. The first payload byte, instead of being supplied by the responder, is actually supplied by the controller as the register index to read from the sensor. So essentially, it changed the meaning of that read bit. It no longer indicates it's a read transaction, but a read operation to that sensor. And this is a violation of the transaction abstraction of the protocol. And this is only one example. In the wild, there's more devices that have I2C quirks. Even your Raspberry Pi I2C controller have quirks. There are CV records assigned to I2C issue, and the Linux source code also contains an array of non-I2C quirks. So we discovered this situation when we built our own computer engine. So this situation and the inability of existing existing device driver motivate us that, okay, let's take a step back, sit down, try to specify what the drivers should do, what the device expects, try to verify them, and finally try to get some useful driver code from that. And toward that goal, we develop Efeu, a framework to generate efficient, verified hybrid hardware-software drivers for I2C device. So the first step to use Efeu is to specify the whole system, not only the controller, but also the responder. So we specify the system, specify the I2C stacks in layers. First, this is how the protocol described, the standard described this protocol. And second, by specifying the stack in layers, we can reuse layers to model non-compliant device. So recall that the AS5011 health sensor violated transaction abstraction, but all the layers below can actually be reused without modification. We only need to build specialized transaction layer and above, and then glue these two parts together. In this case, we can model the non-compliant device with minimum effort. And to be more specific, Efeu use a top-down approach. So first, we specify layers and their interaction using a very lightweight domain-specific language, ESI. So here we show an example of the layer electrical, which is the two wires, and the symbol layer, which encode the 4 symbols. And the interface between them is pretty simple. It's just the electrical level on those 2 wires. And after we specify the topology, we specify each layers as coroutine or finite state machine in another subset C DSL called ESM. So we deliberately make this language a subset of C so that we can use the existing infrastructure, specifically LLVM, to do the parsing and all the static type check, and also the user gets some very nice error and warning message from it. And I would like to draw your attention to this 2 torque derivative on the right. So this torque derivative are coroutine switch. They accept the argument as the value to be passed to the other layer, wait for the other layer to do the work, and then get back the result, and then resume from that. Essentially, this is synchronous call. And we specify the I2C stack, and then the Efeu compiler can translate this ESM code to Promoter code, which is the input language for the spin model checker. And then the spin model checker can do the model checking and check if there's any leaf log, dead log, and whether all the functional assertion pass. Due to time limitation, I will leave out the detail of this verification. And in the paper, we have a lot more detail, including the scalability of this model checking. And once the developer is happy with the specification, the Efeu can take the same specification and generate C code. This C code backend essentially to perform and rewrite on the ESM code. And after combined with the boilerplate code, it generates the software driver stack. And we specify the system, we get some software code, and at a very low level, we connect it with a GPIO driver, basically do the bit spanning. And it works, except that it is very slow. So we target I2C fast mode, which is 400 kilohertz, and this mode is supported by most I2C devices. The generated driver can only achieve less than 200 kilohertz. But if we look closer, actually this is not due to the inefficiency of generated drivers. Yes, this driver also consumes the whole CPU as well. But if we compare with the Linux built-in Big Bang driver, we see a similar performance, like they both only achieve less than 200 kilohertz. And this motivates us to add another backend to the Efeu compiler that generate hardware description language, which can then be programmed onto programmable hardware like FPGA. So on our Enzian computer, our own BMC is a Zinc ultra-scale SoC. It has an embedded FPGA, which arguably is slightly more powerful than common BMC. But as we see previously, the industry is also putting customized hardware root of trust into those BMC modules. So we expect this generated hardware will be useful. And one cool thing of Efeu is it is able to drive the C backend and the HDL backend at the same time and generate this hybrid hardware-software driver. And the interface between them is generated automatically at compile time. The user can specify the split point between the software and hardware parts using just an compile time option, and the Efeu compiler will take care of it. So there's no change to the spec at all. And using this hybrid driver, we are able to achieve a better performance. So here, from left to right, we move layers after layers into the hardware. So the leftmost one, the electrical, is purely software-based driver. And if we move transaction layer and below into the hardware, we are able to reach almost 400 kilohertz. And this generated driver has a comparable performance with the Xilinx I2C IP, which is an hardware IP crafted by human experts and has a similar abstraction level as our transaction layers. And if we put all layers into hardware, like on the rightmost EEP driver, we are able to achieve even better and more stable performance. And in terms of CPU usage, if we use interrupt, we are able to limit the CPU usage to a very low number. And regarding the FPGA resource utilization, here we show a diagram where the colors are the utilization breakdown by layers. And here is the lookup table utilization of the generated drivers. So our transaction driver, which has a similar abstraction level as the Xilinx IP, consume a bit more than 2 times of lookup table. So we believe this is a reasonable number when comparing a generated driver with a IP crafted by human experts. And although the difference look big in absolute number, actually, when comparing with the available resource on the boards, all of them are just nothing. And even if we put the whole stack onto the FPGA, like on the rightmost, we consume less than 1% of the available lookup tables. So yeah, yes, here is just a plot that show off that we actually implement the whole thing on the hardware and using an oscilloscope to measure the waveform. And we show that the hardware-based driver below is actually faster than the software-based drivers. And with Efeu, we get some very trustworthy and very efficient drivers for I2C device and a glimpse into the future. So one way to go is to extend this stack vertically. For example, onto SM bus, a protocol based on a protocol built on top of I2C. Or even we can reach further into the BMC control logic like temperature feedback loop. And another way to go is to introduce more way to talk or communicate between layers. So currently, Efeu is able to allow the layers to talk across the software-hardware boundary, but we can also envision like allowing layers to talk across the process boundary or even the VM and the host OS boundary. In that case, we can create drivers with better complementarizations. Yes. And yet another way to go is to build stack for other protocols such as SPI or CAN. There are also low-level protocols that used in the board management controllers. And similar to I2C, they also have multiple abstraction layers, so we believe they are a good fit for Efeu. And yes, we open source everything, like Efeu compiler, the I2C models, and also the FPGA design. They are all open source, and if you are interested in Efeu, like also, other application idea, and even taking the Efeu idea to broader application, feel free to talk to me. And if you are interested in this idea of putting out hardware dump file, we have a lot of people from the group here. Like you can talk with my colleague, and also Morthy is here. Yes. And that concludes my presentation. I'm happy to take questions. Thanks.